I'm projecting right now. Can you guys see that? Okay. Somebody said yes. Okay. Uh, I want to welcome you to my lecture today, and the topic of the discussion actually going to be F test. Okay, it's going to be F test and Basia F test. Okay, so in regression analysis, we got different kind of tests. Okay, we got different kind of statistical tests that we normally want to figure out. Okay, so our attention today will be on how do we conduct an F test and partial F test, and under what condition, or why do we need to have an F test and partial F test in regression analysis. So we're going to answer the question of why F test and partial F test and how we are going to go about it. Okay, so that is going to be the focus today. Okay, so I want us to start with a simple linear regression. Okay, we actually want to look at F test in simple linear regression. Okay, so looking at F test in simple linear regression, I actually want to make use of the data set that we used before that has to do with the runs time and the run size. Okay, it's a production data that we've discussed before. Okay, you know, we find ourselves in a company where we are into production and we are actually producing different sizes of items. And you know what? The different sizes of items actually take a different time to run. Now, it means we are actually want to fit, it means we actually want to fit a relationship between the run time and the run size, where we actually want to predict the run time from the run size. Okay, you know, it's just like if I have a particular run size, what time is actually going to take to complete that. Okay, and then we have this scatter plot right here between the two variables under investigation. Okay, now of course, symbolically, the predictor is run size, which is X, and the response is run time, which is Y. Okay, uh, of course we're going to have hypothesis. Okay, we're going to have hypothesis, and let me tell you this: in any scientific investigation, we normally state our hypothesis because hypothesis actually depict practical questions, research questions that we actually want to provide an answer to. Okay, so the hypothesis under review, under investigation, is that if I have a simple linear regression model between the response and the predictor, and the response in this case happens to be runtime, and the predictor in this case happens to be run size. Of course, you know, the model I'm actually going to have is going to be y equal to beta naught plus beta 1 x. Now, the beta 1 actually is a regression slope that will actually tell us the rate at which the response is actually going to change, which, you know, with regard to change in the predictor. Okay, and you know the significance of testing for beta 1 equal to 0. Because if beta 1 equal to 0, then it's trying to say that there is no connection between the two variables under review. But when beta 1, what I have here is trying to say that beta 1 is significantly different from 0. But what I have here is that beta 1 is not significantly different from 0. And before we go into research, we got an expectation that, okay, there should be a kind of a linear relationship between the two variables. So to be able to test whether what we have in mind actually coincide with the empirical analysis of the data set, and we're actually going to carry out this test for this hypothesis. Okay, so of course, you're actually going to see something right here. We want to look at what is the practical meaning of beta 1 equal to 0. In a linear regression model where I got a beta y equal to beta naught plus beta 1x. If beta 1 equal to 0, what am I talking about? If beta 1 equal to 0, then I'm actually going to have y equal to beta naught. And that is more or less like an intercept model. So it means what we're trying to say is that the null hypothesis right here is actually talking about the intercept model. So why is that called intercept model? It's actually called intercept model because of the fact that the beta 1 equal to 0, and the only thing that we have in the model is beta naught. And that is why it's called an intercept model. Okay? So, and you know what? That implies if I'm actually looking for the conditional mean of the response given a certain value of the predictor, then that is more or less like a beta naught. So in a beta naught model, in an intercept model, the expected value of y given x equal to small x equal to beta naught. So what we're trying to talk about, is that, okay, the average time, using the data that we're using right now, the average time that it takes to run, a particular item, given the run size is more or less a beta naught. That's exactly what we're trying to say right here. Okay, if it is equal to beta naught, and you actually know that beta naught is constant, right? The beta naught is constant, right? So what we're trying to say right here is that there's no connection between the run time and the run size. So what is implying right here is that on average, it's actually going to take the same time. It's actually going to take, the same time to run different sizes. Okay, I'm going to say that again. So what the intercept model actually try to talk about here is that on average, it's actually going to take the same processing time or the same run time for different kind of run size. That's what it's trying to say. Okay, so that is where the beta 1 is not significantly different from 0. Okay, now but in a situation where the beta 1 is significantly different from 0, okay, then we can actually, if we want to figure out the average of the response given the predictor, and that is going to be a random variable, we're going to have a different result, okay, because when I have a run time, when I have a run size, when I put a run size, I'm actually going to get different averages, for different run size. Okay, so in this situation right here, it shows that there is a connection, there is a relationship between the run size and the run time. But so which means the hypothesis that we have right here, the hypothesis formulation that we have right here. The non-hypothesis that I call the H naught is actually representing the intercept model. Why the alternative hypothesis is the one that is actually representing the full simple linear regression model. So, and that is the reason why I'm going to call that a full model, okay? Why the other one is an intercept model, okay? So the intercept model right here more or less look like a partial model, okay? This is more or less like a partial model, okay? Why this is a full model, okay? And you know what? In any statistical investigation, we are in a world where we actually want to decide between this and that, okay? We actually want to see if intercept model can solve my problem. Why do I need to go for full model? And if a full model can solve my problem, there's no problem. So the most important thing is we actually in a situation where we got several competing models. Okay, we need to be able to investigate to be able to arrive at the best model at the end of the day. Okay, and that is the analysis. That is what we're actually going to be doing. Okay. Now, in a situation where I want to test this hypothesis, okay, in a situation where I want to test this hypothesis, I actually need a test statistic, okay? I need a test statistic to figure that out, okay? Now, the test statistic is actually going to be F test statistic, okay? And this is going to be the formula that we're actually going to use, okay? Now, if you look at the formula right here, you remember the other time when I was explaining the decomposition of the response variable. In one of the lectures that we've done, we did something on decomposition of response variable. I show you how the response variable can actually be partitioned, can actually be splitted into various component of variation. Okay, because we know that the response variable actually have total variation around it, okay? And partitioning or decomposing the response variable into two components, we're going to decompose that into what we call explained variation and into what we call unexplained variation. The explained variation is the same thing as the sum of square reg. Explained variation is the same thing as the sum of square regression, okay? Unexplained variation is the same thing as RSS, which is the residual sum of square. So what we have in this formula right now, what we have in the test statistic formula right now, what we have in the F test statistic right now is the explained variation and the unexplained variation and the sample size. The N right here is the sample size. Now, I told you when I started this course that if you really want to understand any mathematical related subject, you actually need to understand notations, okay? What notation represents, what each notation represents. And that is the reason why right now I'm trying to tell you what is the meaning of each of these notation that I have in my formula, okay? If you really understand each of the notation that you have in your formula, everything is actually going to be good. You will better appreciate, that will enable you to appreciate what you are doing, okay? So what I'm trying to tell you right now, what I have in my F test statistic formula, to test between having intercept model or the full model is what I have right now, okay? And where the SS reg means sum of square regression, and it's the same thing as explained variation. And the RSS means residual sum of squared, which is the same thing as the unexplained variation. Okay, and n right here is the sample size. Okay, and why do I add the n minus 2? Okay, the n minus 2 that I have right here is the degree of freedom of the unexplained variation. Okay, the degree of freedom of the error. N minus 2 is the degree of freedom of the error, and that's why I'm using n minus 2 to divide residual sum of square. Okay, one right here is the degree of freedom. You know, when you are talking about simple linear regression where you got two parameters, the beta naught and the beta 1, then the degree of freedom is going to be 2 minus 1, and that's why you have 1 right here. Okay, if I want to test between if my full model is multiple linear regression, of course, you expect the number of parameters to be more than 2, and you're actually going to take 1 away from that. Okay, so I'm trying to explain the test statistic formula that we actually want to, we want to use right here to figure out a statistical testing on whether we should agree on using the intercept model or the full model. Okay, the next thing I want to talk about is what is the probability distribution of my test? I want to tell you this: anytime you have a test statistic, anytime you are conducting an hypothesis testing, where you actually want to use a test statistic, I think you need to be able to answer a question that has to do with the probability distribution of the non-hypothesis. The probability distribution of the non-hypothesis right now, the probability distribution of the test statistic right now under the non-hypothesis is going to be F distribution, because I'm actually using an F test statistic. Okay, it's just like if somebody committed an offense in the state of Minnesota, okay, the accused person will actually be tried under the Minnesota law. Okay, if somebody committed an offense in Canada, okay, the accused person will actually be tried under Canadian law. Okay, so if we are carrying out a test, what we're doing right here is synonymous with what happened in the court of law. Because we want to pretend as if we're in the court of law right now, where we are trying to test between having declared for intercept model and declaring for full model. Because at the end of the day, we're actually going to take a decision on rejecting one and accepting the other. And that is the reason why, if I have defined my test statistic, I actually need to know what is the probability distribution of the test statistic under the non-hypothesis. Okay, so the probability distribution of the test statistic under the non-hypothesis is actually going to be F1, n minus 2, which means I'm actually using the combination of the degree of freedom in the expression. Look at that. The degree of freedom here is 1. I got a 1 here. The degree of freedom here is n minus 2, and I have n minus 2 right here, because when you look at the F distribution has 2 degrees of freedom. Okay, there are 2 parameters in the F distribution, and the parameters are 2 degrees of freedom. So what I'm trying to tell you right now, this is the first degree of freedom, and this is the second degree of freedom. Okay, and then what I'm trying to draw right now is just to show you the curve of that distribution that we talk about. Okay, now my n is, the data set that we're actually using right here, the sample size is 20. Okay, if I subtract 2 from 20, I'm actually going to get 18. Then it means I'm going to have 1,18. So the density curve for that is what I'm showing you right here. And what you can see right here is something that is skewed to the right. This is a positive skewness. Okay, so different values of different combination of of degree of freedom will actually give us a different shapes. Okay, and because of that, we can see that F distribution is flexible, and that is why it is very, very useful in statistical analysis. Because the moment I change the parameters, the moment I change the degree of freedom, I'm actually going to have a different shape. Now, of course, some of you may be wondering, why do I need to figure out, why do I need to know the probability distribution of the F's of the test statistic that I'm actually using right here? Because it should be impossible to compute a p-value if you don't know the probability distribution of your test statistic. Okay, so because if I want to determine the p-value of the probability distribution of the test statistic, then I actually need to be able to know the probability distribution of my test statistic to be able to do that. Okay, so what I'm actually going to be doing is actually going to be, if I want to figure out the p-value, I'm actually going to do what is the probability of the F distribution given given the 2 degree of freedom that I talk about greater than the realized test statistic. Okay, we're actually going to be looking for a situation whereby the probability of of the F distribution, given the 2 degree of freedom, will be greater than the realized value, the value that we got after computing this one. So in the example that we're treating right now, concerning the run size and the run time, okay, when we compute this, we actually got 48.7. Okay, we actually got 48.7. I showed you the other time how you can have access to sum of square reg and the RSX. Okay, and it's something that we can also compute. Okay, so I'm still going to show you how that can be done. But you know what? If I've used this formula right here on the data set that we have, this is what we got. We got 48.7. Okay, and the question now is, can you identify the p-value in the graph? Okay, can you identify the p-value in the graph? Of course we can do. Of course you can actually find the p-value. But let me tell you something. When you use R software, automatically you're going to have access to all that. In fact, I'm going to show you in the arrow outputs where the p-value is actually computed automatically. Okay, some of you may be wondering, in our previous lecture, we've carried out a significant test on beta 1 before using the t-test, but right now we want to carry out a significant test on beta 1 using the f-test. Now the question now is, can we have a way to compare the two? Are we likely to take a different decision, or is it going to be the same decision when I decide to use a t-test for beta 1 or I decide to use an f-test for it? Okay, and I want to believe at the end of the lecture today, you're actually going to see the similarity between the two, or if there's any difference at all. Okay, now there's I told you before that when you run um, a linear regression model with an R software, you're actually going to have this, right? This is your output. Okay, and you know what, if you want to test the significance of beta 1, okay, if you want to test the significance of beta 1, okay, using the t-test, of course, this is where you're going to come. This is going to be your test statistic, right? The test statistic value. Okay, when you are testing the significance of beta 1 using t-test, that is why this is coming under a t-value. Okay, and I told you how I got this. Is going to be this divided by that, right? And this is the p-value associated with that. Okay, so right here, this is trying to tell us that, okay, the beta 1 is significantly different from 0 using the p-value right here when you compare with the 0.05 level of significance. Okay, but in a situation where I want to use an F test, okay, if I want to use an F test, okay, using the formula right here, okay, using the formula right here, if I want to compute an F test, I want to tell you, look at the result right here. Arrow has already computed that for you. Look at that. F statistic is 48.72. This will be automatically part of your result. Okay, when you run that in R. So this guy here, 48.72. Okay, the formula to figure this out, okay, is what I'm trying to show you right here. Okay, this is the formula. But you know what? Arrow will automatically compute that for you. Okay, and you can see this particular formula is telling you that it's based on degree of freedom 1 and 18. It's based on degree of freedom 1 and 18. And let me show you here. Look at that. It's based on degree of the whole thing here is based on degree of freedom 1 and n minus 2. And the number of observation here is 20. Therefore, it's going to base on degree of freedom 1 and 18. And that's why you have 1 and 18. Okay? So, and that was why I put the value here that, okay, that was what we got, 48.7. How do I know that? Of course, it's actually from here. So when you have your output, okay, your F statistic value is this, and it's based on 1 and 18 degree of freedom. And you know what? You know, I talk about p-value. Okay, I talk about getting a p-value associated with the F statistic, and the p-value is actually here. Look at that. Look at the p-value here. So there's a difference between the p-value here and the p-value here. The p-value here is the one that is a p-value associated with the t-test on beta 1. But why the p-value here is a p-value associated with a significant test, you know, using the F test, okay, on beta 1. So the fact remains, whether we're talking about this or we're talking about this, we're carrying out a significant test on beta 1, okay? But only that here we are using a t-test to be able to figure that out, but here we actually use an F test to be able to figure that out. And that was the reason why I got this extraction out here, okay? So as you can see right here, the t-test statistic is 6.98 that I extracted from here, okay? And what is the p-value associated with that? Is this guy here that I put right here. And in the case of the F statistic test, you know, is the one that I put right here, okay? Is the one that I actually put right here, okay? And the p-value associated with that is what I put right here. And let me tell you something, some of you may be wondering, is there a connection between the F statistic value and the test statistic value? And I want to tell you there's a connection between them, okay? The F test statistic value is 48.72, and this is 6.98. But do you know that when I square, it is when I square this, then I'm going to have this, okay? So the square of this is approximately this. And that is the reason why this actually confirmed the theoretical, you know, the proposition in statistics that said when I square t, I'm actually going to have f. Okay, the square of when I square t, then I'm actually going to have f distribution. Okay, so when you square this guy here, which will automatically give you this, and that is the connection they have. But based on what I'm doing right now, the two of them actually they are taking the same decision. Okay, is there anyone who need clarification on the comparison between the t-test for beta 1 and the f-test for beta 1 in simple linear regression before I go ahead? Is there anyone? Okay, in the absence, I think silence implies that you guys are good. Are you guys hearing me? Okay, I'm going to read my chat. Let me read my chat. Okay, yeah, you guys can hear me. Okay, I think I got that information now. Okay, so uh, like I said, the two of them are actually equivalent. Okay, the two of them are actually equivalent. Okay, now uh, I want to have another example right now. Do you remember with my professor data set that we used the other time? Where we talk about, I think I could remember we use two variables, the clarity and quality. Okay, so I want us to revisit the data set now. We want to revisit the data set now. But you know what? Uh, this time around, we want to look beyond the variables that we considered the other time. You know, like I said, we get different kind of variables. When students are rating their professors, actually, there are different kind of variable the student will actually need to comment on. Okay. In the rate by professor, we got what we call quality. Okay, the quality rating of an instructor. Okay, it's actually going to be between 1 and 5. Of course, if a professor is rated 1, is worst, and if rated 5, that is best. Okay, and that's what we also call easiness. It's one of the variable, and the easiness rating is also between 1 and 5. Okay, it's from 1 to 5. Okay, and that's what we call paper. So yes means the instructor is hot. Okay, no means the instructor is not hot. Okay, so these are variables that I want us to analyze today. Now, the difference between what we're doing now and what we did before was that before we only focus on two variables where we fitted simple linear regression, and the two variables we considered them was quality and clarity. Okay, but today we are actually going to be changing. We're still going to use the same response variable, quality, but we're going to have new predictors, easiness and Pepe. Okay, easiness and Pepe, and you know what? The Pepe is categorized. Okay, the one of the predictor here is categorized. Okay, so of course yesterday I think I walk you through the combination of I walk you through the combination of you know having uh, categorical predictor and a quantitative predictor. Okay, somebody said a quick summary of yesterday would be okay. Yes, excuse the first part. Yeah, we can. Oh, okay, okay. Thank you for that. So, if you look at the graph that I have right here, you're actually going to see that this is a plot between the quality and the easiness, and at the same time putting into consideration the Pepe. Okay, and you know the color what I have here is indicating no. Okay, why this is yes. Okay, now if I have this right now, the number of students that was involved in the rating, I think it's 366. Okay, or let me say that 366 professors were, yeah, 366 professors were actually rated by students. Okay, now from based on what we have, okay, uh excuse me, now based on what we have, we actually want to have, you know, a F test. Why do we want to have a F test? We actually want to have, oh, excuse me, give me 1 second. I think that should be okay. We want to have an F test using the rate my professor. Okay, but this time around, of course, uh, Y is going to be quality, that is in response. The X1, of course, we have two predictors. The X1 is easiness, and the X2 is pepper. Okay, of course, this uh, it means we are likely going to be fitting a multiple linear regression. Okay, so which means we are no longer fitting simple linear regression. Why? Because we got more than one predictor. Okay, now, and that was why I canceled, the simple right here. Okay, that was why I canceled the simple right here. Now, if I want to talk about quality, okay, the expected value of quality, okay, if I take on, before I can consider an intercept model, is when, okay, there is no connection between Y and X1 and X2, okay. The expected value of the quality is actually going to be equal to beta naught. And for a situation where that is going to happen, I'm going to explain right now. Now, how many regressors are we going to have in this? If we want to consider this, how many regressors are we going to have? We're going to have 3 regressors. Okay, we're going to have 1, we're going to have X1, we're going to have X2. I'm going to say that again. How many regressors are we going to have considering this model right here? We're going to have 1, we're going to have X1, we're going to have X2. Okay, so 1 is the intercept of beta naught. X1 is the intercept of beta 1. So like what I want to do right here, I actually want, I've been using beta naught and beta 1. In another model, I can say, okay, I can use beta 1 as an intercept. It doesn't really matter. Okay, now take a look at this. The beta 1, the beta 2, the beta 3, the parameters associated with the predictors and the intercept itself. So when you look at under the null hypothesis, when the parameters of the regressors, the beta 1, the beta 2, the beta 3, if it is equal to 0, automatically I'm actually going to have an intercept model. Okay, I'm actually going to have an intercept model. But in a situation, where that doesn't really happen, now I want you to look at something right here. Okay, I want you to look at something right here. Let me explain the situation to you so that you will really understand what I'm talking about. We want to consider 2 models, and these are the 2 models. I'm still going to use beta naught to represent intercepts, but you know what? In my full model, I'm actually going to have easiness, pepper yes, then they are linear, then they are combination. Yesterday I talked about interaction, right? Now, this is going to be my model. Now, what happened in my model now? I'm actually going to have a beta naught, the beta 1, the beta 2, the beta 3. Now, let me explain each of these. I'm going to explain each of these. Okay? I'm going to explain each of that. The beta naught is the intercept. The beta 1 is the contribution of easiness to the model. The beta 2 is the contribution of the categorical predictor. And that was why I wrote pepper yes. Okay? Because when pepper yes equal to 1, I'm actually referring to yes. When pepper yes equal to 0, and then I'm referring to no. Don't forget that the pepper here, I'm going to walk you back now so that you'll be able to see the nature of the pepper yes that I talk about. Look at that. The pepper is categorical. No, yes or no. Okay? When I write pepper yes, then it means that variable, that predictor is 1. When you understand now? And Pepe yes equal to 0 means I'm talking about no. Pepe yes equal to 1 means I'm talking about yes. Okay? So just take note of that. Now, just like what we did before, what we are actually testing, okay, in the model now, what we are testing is the intercept model is going to be beta naught. Okay? What we're trying to say is that the average quality of a professor, okay, the average quality of a professor is constant. Okay? It doesn't really matter. It does not have any connection with easiness, Pepe, and the interaction between them. That's what we're trying to say right here. Okay, I'm going to say that again. The intercept model here implies that the average quality of professors, average quality of professor is constant. Constant means you know it doesn't depend on easiness, Pepe, and their interaction. But when you look at the full model is trying to tell us that the expected quality, which we call the average quality of any professor, can actually be determined if we have information about the easiness, information about the purpose, information about the interaction of the two. Okay. Now, if the hypothesis that will correspond to this, the hypothesis is actually going to be this. In that situation, it means the beta 1, beta 2, beta 3 equal to 0. And don't forget, the beta 1 is a contribution of easiness. The beta 2 is a contribution of the Pepe, and the beta 3 is a contribution of their interaction. So in a situation where the beta 1, the beta 2, the beta 3 equal to 0, automatically the full model will actually reduce to the intercept model. And that is so this is the hypothesis, this is the alternative hypothesis for this. What we're trying to say, at least one of these is not 0. That's what we're trying to say. So, but here, all of that are 0. Okay? And that's exactly what we want to test. Okay, so if we want to test that now, of course, this is going to be the F statistic value. Of course, how many parameters do we have in this model? 1, 2, 3, 4. Okay, we got 4 parameters. I'm going to say that again. 1, 2, 3, 4. Okay, therefore the degree of freedom is going to be 4 minus 1. And that was why I got 3 right here. Okay, and this guy here is still going to be what we have. So now, initially we said n minus 2, right? The degree of freedom for residual, okay, the degree of freedom for residual as well is actually going to change. Okay, it's going to change. We can have that. We have n minus 4. And why do we have 4? Of course, we got 4 because of the fact that the number of parameters here is equal to 4. 1, 2, 3, 4. And if I were you, if you take a look at what is happening here, whenever this is 3, this is actually going to be 4. So this is going to be 1 more than this. Okay. Now, in that situation, now we can actually compute this. Okay. Now that is actually going to change. Look at what we have. So because this is going to change to a new shape, because what we're going to have now is going to be the combination of 3 and n minus 4. And at n is 366. I think you know that. I'm going to walk you back to be able to see what I talk about. 366. The one for it, my professor. Oh, okay. Can you see that here? 366. And by the time you plug in 366 minus 4, so you're going to have 3 against 362. So of course you are not going to have this again. You're going to have a different shape. Oh, can you see the shape right now? This shape right here is different from the one we did before. Look at that. Can you see that now? Okay, so now how do we write our code to figure out the data? Of course, this is the way we're going to write the arrow code. Okay, we're actually going to have the easiness, the pepper, and yesterday I was talking about main effects, right? So this is the main effect. The easiness is, we can look at the main effect of easiness, we can look at the main effect of pepper, and we can also look at the interaction effect. And of course, the data is rate profile, prof. Okay, when I do this summary, oh, this is what we have. Okay, this is what we have. Okay, of course, you can see the estimate of beta naught, you can see the estimate of beta 1, you can see the estimate of beta 2, you can see the estimate of beta 3. Okay, and I told you when you have the pepper years that you see here, we are assuming when the variable here is categorical. Okay, when pepper equal to 1, then we are referring to yes. When pepper equal to 0, we are actually referring to no. Okay, that's exactly what we're trying to say. And this is the interaction between them, and this is the estimate. This is the corresponding standard error, and this is the t-value, and these are the p-value. Okay, and you know what? If you want to look at the significance of the overall model, okay, of course, this is the F statistic for that. So what I'm trying to tell you right now, the 75.29 that we have right here, we use the formula here. We use this formula here to figure that out. Okay, you can use the formula here to figure that out. Okay, and that is the value we have here. And what I have here is the corresponding p-value. Okay, for that, this is the corresponding p-value. So the p-value here will enable you to take decision regarding the F test. Okay, we enable you to take decision regarding this hypothesis that we're testing right here. Okay, so that will enable you to take that decision. But the p-value that we have right here will enable you to take decision regarding the intercept, regarding the easiness, regarding this and so on like that. Okay, now let us now have a conclusion on the F test. I'm still using the data set rate my professor. Of course, you know, this is our output. Okay, and when we have an output like that, of course, we actually need to know how to interpret our results. Okay, so when you succeed in running your analysis and you have a result like this, of course, we should have a way to interpret our results, okay, in line with the goal of the study. Can you guys hear me? Can you guys hear me?
Yes.
Okay, thank you so much. No, I'm just trying to be sure. And of course, technically, you know that when p-value is small, okay, when p-value is small, it's actually going to favor the alternative. Okay, when p-value is small, it's actually going to favor the alternative hypothesis. Okay, because when p-value is small compared to the level of significance, you're actually going to reject. Okay, and that means when you reject this, you are in favor of the alternative. Okay, when p-value is small. But when p-value is large, of course, it will favor the norm. Favoring the norm means it's going to favor the intercept model. So what I'm trying to say, that is technically, and that was why I said the small p-value lead to the rejection of the null hypothesis. What are you rejecting? You're actually going to reject the intercept model. Okay, and rejecting the intercept model means that the full model fits the data significantly better than the intercept model. That's exactly what we're trying to say. But the question now is, how small is this? Is small? Of course, small in terms of you're actually going to compare your p-value with a given level of significance. The level of significance is actually, we got two levels of significance that we normally use, 5% and 1%. That is a 0.05 and a 0.01. Okay, but what we use most of the time is a 0.05. So when the p-value is less than a 0.05, then you're actually going to reject the null hypothesis. And of course, the null hypothesis is talking about intercept model. The null hypothesis is talking about situation whereby, you know, there is no relationship at all. I cannot predict the quality of a professor from either from the main effect or variable or from the interaction. Okay, but the alternative is actually going to say I can actually do that. So in the context of what we're trying to say right now, of course, we're actually going to have a conclusion that there is a linear association. When I say linear association, I mean linear relationship. I mean there's a connection between an instructor quality rating and his or her easiness rating of physical attractiveness. Okay, so easiness rating, okay, of physical attractiveness. You know, that's what I'm trying to do. Because let me tell you something. I could remember the first time I set into, I remember in 2018, September 2018, when that was the first time I set into a class to teach at the University of Minnesota in the United States, okay? Because I got most of my teaching experience that I got was from Africa. I want to tell you the first time I sat into a class to teach at the University of Minnesota, I saw about 4 students that walk out of my class. You know, merely, you know, they saw my, you know, maybe I was not that attractive enough. Maybe, you know, some of them may be expecting somebody of different color. But you know what? Over the, you know, days, you know, when I've been teaching and some of them saw what I was doing. Oh, this guy have a kind of different color from us, but this guy can actually teach, okay? And and that is why some of them that were not coming to my class before, they were you know, they were now coming to my class. That can happen, you know, it's natural, okay? It's natural. You know, attractiveness is very physical attractiveness. Okay, physical attractiveness is very, very important. Okay, when we come to teach, the way we dress matters a lot. The way we look matters a lot. Okay, because even if you want to teach something great, but your appearance, you know, may not, you know, the student may not like one's appearance. But you know what? The moment you appear so good and you convince people that, oh, you can actually deliver, I want to believe you're actually going to attract a lot of students to yourself. Okay? So I want you to look at the model. I want you to look at the results. Okay? You can see the intercept is significant, the easiness is significant, the pepper yes is significant. It means the takeaway from what I have here is that the main effects are significant. Main effect. When I say main effect, I'm referring to easiness separately. I'm referring to the pepper yes separately. But look at the interaction effect. The interaction effect is not significant. Okay? The interaction effect is not significant. Okay, and so you can see that right now. Okay, so that because the level is 0.05, you know, the p-value here is actually a little bit actually less than any reasonable level of significance. Okay, if you want to use at 0.05, you know, you are in a kind of a dicey situation. What I have here is more or less greater than, slightly greater than 0.05, and that doesn't make it to be significant. Because if you look at it from 0.01, this is far greater than 0.01, and the interaction in this model doesn't really work. And I told you the other time, it is not all the time that interaction, you know, including interaction in a model may actually impart. So here, it does not make sense adding interaction in this model because the effect of that is not significant. But looking at the model in entirety, the model is good. Okay? Because the p-value here is the one that is associated with the F statistic value here. The model is adequate. The model is good. But which means with this p-value, we are actually going to reject. This hypothesis. And you know what? The hypothesis here, the alternative here, does not mean that all parameter is not equal to 0. It's trying to say at least one of the parameter is not equal to 0. It's not saying all. Okay? And because if it is saying all, if this is saying all, then we expect everything to be significant here. We expect everything, we expect this interaction as well to be significant as well. Okay? So what we're trying to say, the fact that this is significant does not mean that everything here is going to be significant. That's what I'm trying to tell you right now. Okay? And I told you before, the entire test, this is the degree of freedom. You know, don't forget that we use n minus 4. 366 minus 4 is 362. So this is the degree of freedom for the error. Okay? This is the degree of freedom for the error. And right here, it is n minus 4. And why minus 4 is because I got 4 parameters. You know, 1, 2, 3, 4. Okay? So 366 minus 4. That was why I got 362. Can you see that now? And this is the residual standard error. And what I have here is a multiple R squared. Okay? Though the model right here is good, is adequate because of the fact that the p-value is less than 0.05. But you know what? This model is not that good. It's not that good because what I have here, it has a very small R squared. This is small. This is like it's about 38% in the variation in the response, has been explained by the model. So this is a poor model. Okay. Like I said, the model is adequate. How do I know the model is adequate? Because the p-value is less than 0.05. The model is adequate. But you know what? The degree of adequacy of this model is very, very small. Okay? There's a difference between a model is good, a model is adequate, and now trying to look at the degree of adequacy. So though the model is good, but the rate at which this model is good, the degree of the adequacy of the model is very, very small. Okay? So which means the model can still be improved upon. Okay? That is if everything is good. Okay? Now, technically, based on what I said before, I think I've explained this to you. The reason why I took this decision, of course, judging by what I saw in the in output. Okay. Now, looking at that again, of course, I've explained this to you. Okay, that this is the F statistic value for the test, and these are the degree of freedom, 3 and 362. Of course, you know how I got 3, right? That's I got 3. That's 4 minus 1. Okay, 4 minus 1, and this one is n minus 4. I think you know that, and this is a p-value associated with that. Now, the question we want to ask right here, is there an equivalent t-test to this f-test? That is the one I underline here. The other time, we look at the equivalence between the t-test and f-test when you are looking at, when you are carrying out a significant test on beta 1. But now that we have an interaction model, okay? Now that we have an interaction model, is there an equivalent t-test to this f-test? So that is what we want to answer right now. But before we go to answer that, I need to for us to walk you through a diagrammatical explanation of that. Okay. Now take a look at. Let us split this thing into 2. take a look at what I have here. This is quality. Okay. I plotted that against easiness. I'm putting into consideration that the paper is categorical. And this is the center. Take a look at that. This is the center. Okay. The center here is just talking about the mean of the quality. Okay. The mean of the response. Okay. This is talking about the mean of the response. And take a look at this. This is more or less giving us, this is like giving us the notion of the intercept model. You know, but because in intercept model, before I can consider this straight line, it means I'm actually going to get the same value of quality when I increase easiness. Okay, when easiness go up, I'm actually going to get the same amount of quality. Okay. Now, when you take a look at this guy here, okay, you know, you're going to see something different. And that is the reason why here you're going to see that this is not it's not an horizontal line. Okay, not having an horizontal line, you know, the dotted line and the straight line that we have here is indicating the fact that you know, the average quality is not going to be the same. But right here, the average quality is the same. That is why. So this is more or less representing an intercept model. Why this guy right here is actually representing the full model. Okay. Now, why do we have two lines? We actually have two lines because we are actually working on the two predictors. Okay. And do you know one of the reasons why the interaction is not significant? I'm going to tell you right now. Look at it. Look at that. You know, the interaction is not that significant, right? As you can see right here, these two lines, they don't really meet. Look at that. They don't, you know, they nearly, you know, they don't really meet. Okay. You know, it is only when the two lines, when they meet, that you can be talking about whether the interaction is going to be significant or not. Okay, so I want you to see the two lines right there. Okay, so the picture that I'm actually showing you right here is the one that is showing just for you to be able to make a sense out of the picture that represents the intercept model and the one that represents the full fitted model. In the intercept model, of course, the expected value of the response, that is expected value of the quality, is actually going to be the same given any level of the predictor, but it's not going to be the same under the full model. Now let's have a summary of what we have done. Now the F test is testing a very low bar if any of the predictor variable is associated with the response variable. Okay, and that's exactly what we are actually testing. You know, you actually want to use that to measure the relationship between the response and the predictor variable. Okay, now the usefulness now is this. Let's ask a question. Does physical attractiveness, Pepe, affect the relationship, okay, between the quality rating, okay, of a professor? So we want to see that right now. So which means we actually want to compare two models. We want to compare simple model with a complicated model. Okay, in comparing simple model with complicated model, we actually need to state our simple model. Of course, our simple model is actually going to be this. Now, let me tell you this. What we have done before is like comparing two models. We're comparing a complex model with an intercept model. But what we want to do right now, we want to compare simple model with complicated model. And in the simple model, where, of course, this is more like, this is a simple linear regression, where we got a quality and easiness. Okay, we got a predictor right here. Okay, this is a simple model. Okay, now the two paper groups have the same relationship between quality and easiness. So here, there is nothing like partition. Okay, there is nothing like, you know, partition, you know. So here, you know, there's nothing like grouping, okay? And that was why we said the two pepper group have the same relationship between quality and easiness, okay? But in the complicated model, it is not going to be the same. In the complicated model, I'm actually going to have what we just concluded right now, okay? Now, you know, in the F test that we conducted, we actually compare this complicated model with the intercept model, okay? What we just finished right now, we compare complicated model with the intercept model. But right now, we want to move away from that. We want to compare the complicated model with the simple model, okay? The simple model right here. But let me tell you something. Simple model and complicated model, these two models are nested. Let me have a share right now. I'm going to have a share right now. I'm going to share my work. I'm actually going to make use of my dashboard. Can you guys see my dashboard right now? Can you guys see my dashboard?
Yes.
Okay. Now, you know, I make mention of nested model. Okay. Now, what makes a model to be nested? Okay. What makes a model to be nested? Okay. If a simple, if one model, okay, if one model can be found in the complicated model, in the complicated model, okay, if one model can be found in the complicated model, then the two models are nested. Okay, the two models are nested. Okay, if one model can be found in a complicated model, for instance, you got two models that you actually want to compare, and the simple model, if it can be found in the complicated model, then it means the two models are nested. Okay, it means the two models are nested. Okay, now if that is the case, I'm going to go back to, now what I'm trying to tell you right now, these two models are nested. Why are they nested? Because the beta naught plus beta 1 easiness can also be found in this model. Can you see that now? It's right here. So which means this model right here is an extension of this model. Okay, if I want to go from this model to this model, okay, then when beta 2 equal to 0 and beta 3 equal to 0, I'm actually going to go from this model to this model. Okay, therefore these two models are nested. Okay, these two models are nested. Okay, even in the one we did before, the one that we go through before, they are also nested. The intercept is nested in any model. I'm going to show you right now. The one we did before. Okay, the one we did before. Okay, take a look at this. The beta naught here is also found here. Okay, so the intercept model is nested in the full model here, because I can find the intercept model in the full model. In a situation where beta 1 equal to 0, beta 2 equal to 0, beta 3 equal to 0, then I'm actually going to go from the full model here to the intercept model. Therefore, the two models here, they are so nested. Okay, so let me go to what we're doing right now. So, like I said, the two models are nested, and don't forget that we have a paper yes equal to 0. Paper, the paper is categorical. Okay, so when Pepe yes equal to 0, okay, when Pepe yes equal to 0, okay, the expected value of quality is actually going to be this. But when Pepe yes equal to 1, this is what we're going to have. You remember yesterday, I was walking you through something, okay, when I make use of my dashboard. Now, let us focus on this right now. Okay, this is a model, right? Let us plug in 0, where we have Pepe yes. Oh, when I plug in 0 right here, okay, the whole of this is going to be 0, right? And when Pepe yes is 0, I'm also going to plug in 0 right here, right? When I plug in 0 here, the whole of this is going to go away. What am I going to have right now? I'm only going to have this, which is right here. Can you see that now? But when Pepe yes equal to 1, when I put 1 here, hello, when I put 1 here, what is 1 times beta 2? Then the intercept is going to change. The intercept is going to be beta naught plus beta 2. Okay, that is what I have here. Because I've already plugged in 1 here. Okay, and I'm also going to plug in 1 here. Okay, when I plug in 1 here, okay, the slope is going to change. When I plug in 1 here, I'm actually going to have beta 3 easiness and beta 1 easiness. So it's going to be beta 1 plus beta 3 easiness. That's why I got this. Is there anyone who have a trouble time figuring out this one? Is there anyone? Is there anyone? So what I'm trying to say in essence is that the model here, this is the model, okay, for when Pepe yes equal to 0. And this model right here actually coincided with a simple model. Can you see that now? And when it is equal to 1, we're actually going to have this. And I think I show you how we got this right now. Okay? Okay. And that was why we said the two Pepe groups could have different relationship between quality and easiness due to different intercepts or different slopes. Look at that. If you look at the two, this is the first group. This is the model for the first group. This is the model for the second group. Therefore, the intercept for the first group is beta naught. Okay, which group am I talking about? You know, where Pepe yes equal to 0. This is the intercept. But when Pepe yes equal to 1, the intercept has moved from beta naught to beta naught plus beta 2. Look at that. Difference in intercept. Okay, difference in intercept. Okay, and also different in slope. Look at that. Different in slope. The beta 1 here, but beta 1 plus beta 3 right here. Okay, and that is the reason why we said the two Pepe groups could have different relationship between quality, okay, and easiness due to different intercepts or different slopes. Okay, I think you can see that right now. Okay, so using the graph to be able to figure that out, this is the simple model. Okay, this is the simple model. I mean, this guy here, I'm going to show you now. The guy here. Okay, this is the simple model. Okay, now what about the one for complicated model? This is a complicated one. Okay, this is a complicated one. Okay, that's why you got 2 lines. Okay, this is the simple one. Okay, okay. Now, in a situation where we are comparing between simple model and complicated model, okay, because we actually want to take a decision whether we should use the simple model right here or we should use the complicated model. Don't forget, the complicated model actually involve the main effect as well as interaction effect, because we actually want to decide in statistical analysis to be able to, we want to decide on the right model, which one is good for us. Is it going to be a simple model or is it going to be a complicated model? Okay, and that's exactly what we want to do. And to be able to do that, we actually need to fit what we call a Basia F test. Now, if you look at the topic today, I want you to look at the topic today so that you'll be able to see that we are in second half now of today's work. I want you to see the topic for today. Now look at the topic for today. F test and Basia F test. There's a difference between F test and the Basia F test. Okay? The F test was what we conducted before when we were testing between when we're testing about the significance of the overall parameters in the model. And testing for the significance of the overall parameters in the model is just testing between the full model and intercept model. Okay, you use F-test for that. I can ask that kind of question in a multiple choice question in exam. Now, what is the appropriate test? If I want to carry out a test on the overall significance on the overall significance of a model, okay, where I'm testing for all parameters in the model against the intercept, okay, what I'm going to use is the F test. But in a situation where I got two different kind of model and none of them is intercept, maybe one is a simple model and the other one is a complicated model, okay, and in such a way that the simple model is actually nested in complicated model, okay, we're actually going to make use of what we call a Basia F test. So I'm trying to tell you right now, there's a difference between the F test and the Basia F test, and what we have been doing today is the F test, but right now we actually want to go into Basia F test. And when do we use Basia F test? When we are actually talking about comparing between the simple model and complicated model, okay? And what we need to do is to, talk about Basia F test. And that was the reason why I said a Basia F test, hypothesis test that compare two models, okay? It compare two models. Like I said, it compare two models, and in the non-hypothesis, what you're going to see in the non-hypothesis is going to be simple model. And what you're going to see in the alternative is going to be complicated model. So the non-hypothesis is going to assume that the simple model is fine. Alternative hypothesis is going to assume that the complicated model is fantastic. Okay? And and don't forget the condition under which you can do that is that the simple model has to be nested within the complicated model. And I've told you the meaning of a nested. So what we're doing right here, if you take a look at what we're doing right here, the simple model is actually nested here. Look at that. This guy here is inside here. And as you can see, when Pepe here is equal to 0, we can actually go from the complicated model to the simple model. And that is the reason why we got this guy here. Can you see that now? And that is a nested that I talk about, and that is a condition under which the Basia F test operates. Okay, as you can see, the non-hypothesis is assuming this, right? And the alternative hypothesis is assuming this, right? And don't forget that the two models are actually nested in each other, okay? They are actually nested, okay? Now, if I want to carry out a test like that, like I said, you need to be able to state your hypothesis and your test statistic. Right now, we want to decide between a partial model, we want to decide between a simple model and a complicated model. And you know what? Another name I can call a simple model, I can call it a partial model. Another name I can call a complicated model, I can call it a full model. Okay. Now take a look at that. This is what we are testing. Okay, why am I testing for beta 2 equal to beta 3 equal to 0? Where am I testing for that? Take a look at that. The condition under which, you know, we can actually go from here to here when beta 2 is 0 and beta 3 equal to 0, we're actually going to have just this model. And that is the reason why we need to test whether beta 2 is 0 and beta 3 equal to 0 at the same time. So because when beta 2 equal to 0 and beta 3 equal to 0, we're actually going to have a simple model. And that is the reason why we have that hypothesis, okay? Beta 2 equal to 0, beta 2 equal to beta 3 equal to 0. Okay? But right here, the alternative, you're going to say at least one of the beta 2 or beta 3 is not 0. So please know how to specify your hypothesis testing when you are working with a Basia F test. Okay? So the test statistic now in the example, now take a look at this. This is a new formula. The formula right here is different from the one we used before. I'm going to show you under the F test. You can see the formula is different from the one we're using here. Okay, this is an F test. The formula is totally different from this. Okay, we only use this formula when you are testing between a full model and the intercept model alone. Please take note of that. And if I want to write the general formula for this, I'm actually going to write the sum of square reg, okay, divided by, this is the degree of freedom, okay, the degree of freedom of the parameters in the model. If the parameter is 4, it's going to be 4 minus 1. That is why you got 3. And this is going to be n minus p, okay, if p is the number of parameters. So here I'm taking that p equal to 4. The parameter is beta 0, beta 1, beta 2, beta 3, right? Now, take a look at the Basia F test now. The formula is totally different. Okay, you can see the formula is totally different right here, and I'm going to tell you the meaning of this formula right here. This is the residual sum of square, okay, of the simple model. The X here is indicating simple model. This is the residual sum of square of the complicated model. Okay, why am I dividing by 2? I'm dividing by 2 because the number of parameters under hypothesis is 2. 1, 2. I'm going to say that again. Why am I dividing by 2? I'm dividing by 2 because the number of hypotheses, the number of parameters under the hypothesis is 2. 1, 2. Okay, that's why you have 2. Okay. Now, the degree of freedom is going to be n minus 4. Why 4? P. P is 4. I'm going to take that from the complicated model. I'm going to go to the complicated model now. How many parameters do we have in a complicated model? 1, 2, 3, 4. I'm going to repeat that again. 1, 2, 3, 4. We got 4 parameters in the complicated model. And in the formula right here, that is why you have n minus 4. Okay? It's not all the time that it's going to be 4. It's not all the time. You know, there could be something else right here. So just know that what I'm going to plug in here is the number of parameters in the complicated models. Okay? The number of parameters in the complicated models. Okay? Then 2 here is the number of parameters under hypothesis. This is 1, 2. Okay? So, like I said, this is the residual sum of square for the simple model. This is the residual sum of square for the complicated model. This is the residual sum of square for the complicated model. So, like I said, in general, this is the formula in general. Okay? The degree of freedom for simple model, the degree of freedom for complicated, the difference between that. Okay? That is 2. Or you can simply say 1, 2. No problem. And this is the degree of freedom for complicated model. Okay. Now, so that's why I define that as that. Okay. Now, the degree of freedom of n, the degree of freedom of the residual sum of squared, of course, you know, is the sample size minus number of model coefficients, the one I call the number of parameters. And that is why this guy is 4. I think you know that. The parameter is 4 in the complicated model. Okay. Now, under the null hypothesis, we actually need to know what is the distribution. Just like what I told you before, if you want to carry out any test in statistics, you need to know the distribution of the test. So that you need to know this is the distribution of the test right here. Okay, this is the distribution of the test. Of course, you actually need to know the distribution of the test to be able to figure out the p-value. Okay, this is going to be the p-value. The degree of freedom you're actually going to use to figure out the f, the critical f, is actually going to be the this guy here. Whatever you have here and whatever you have here. Okay, that is the degree of freedom. Okay, that we're actually going to talk about. Okay, do you get it now? Okay, so and that was why we got this, right? Okay, so the larger f test statistic value, okay, then the p-value is going to be. Now let me tell you this: when the f statistic value is large, of course the p-value is going to be small. I can ask you that question in exam. Take note of that. Okay, when the f statistic value is very, very large, then the p-value associated with that will be very, very small. And when the p-value is very, very small, then you are actually going to reject the null hypothesis. So take note of that. Okay, that was why I said the smaller the p-value. Okay, when the f statistic value is large, the smaller the p-value. Now, we can use R to run Basia F test. Okay, another name for this test, when we call it a Basia F test, we also call it a nested F test. Nested F test. Okay, you can call it a Basia F test or a nested F test. Now, how do we do this in R? Okay, how do we do this in R? Of course, you know this is your code, right? Okay, this is what you're going to do in R. If you want to do that in R, you're going to have two models. You know, we got two models, right? The code here represents for complicated model, and the code here represents the simple model. Okay, I'm going to say that again. The code here represents the complicated model, and the code here represents the simple model. So if you want to run that in R, you're going to write ANOVA into what whatever you use to save your simple model, comma, and whatever you use to save your complicated model. I'm going to say that again. This is your code in R to run a Basia F test that we also call a nested F test. You need to first write a code for complicated model. You're also going to have a code for the simple model. And when you do that, then you're going to do ANOVA into mode 1, comma, mode. Go. This mode 1 is for simple model. The mode is, and you're actually going to see the results. Now, this is what the result is going to look like. Okay? This is what the result is going to look like. So what you have here, you're going to see analysis of variance table. And in the result, you're actually going to see model 1. It's going to tell you what you have in model 1, which is a simple model. And it's going to show you what you have in model 2, which is a complicated model. And you know what? This is what you should focus on. You're going to focus on this and this. This is the value for the Basia F test that we talk about. Okay, this is the value of the Basia F test that we talk about. Okay, and then if this is the value of the Basia F test that we talk about, this is a p-value associated with the test. Now, this is the residual sum of square of the residual sum of squared of the simple model, and you're going to have the residual sum of square of the complicated model. Okay, the residual sum of square of the simple model and that of the complicated model. This is a F statistic value. This is a p-value. And the p-value right here is less than 0.05, and you're actually going to reject model 1. Model 1, don't forget, model 1 is a simple model. Model 1 is the one that is under the null hypothesis, while model 2 is the one that is under the alternative hypothesis. So the p-value that I have here then suggests that since the p-value is less than 0.05, I'm actually going to reject model 1. And that is going to be the conclusion, because of course the p-value is very, very small. So which means that the complicated model actually fits better than a simple model. Can you see that now? So in the context, the physical attractiveness affects the relationship between an instructor quality rating and their easiness rating. Okay? And that's exactly what we're trying to say, because since model 1 is not true, then model 2 is true. And what makes that model to be true may be as a result of this guy here. Okay? And that's exactly why we are making that conclusion. Is there anyone who want to ask a question? Is there anyone? And remember that initially on page 11, that we are actually trying to answer a question, a research question, that said, does physical attractiveness, which is Pepe, affect the relationship between quality rating and the easiness rating of an instructor? That was the research question that we're trying to answer. And that was what, based on that research question, we actually formulated an hypothesis, okay? And then we analyzed the result, and this is exactly what we have right now. So we've been able to have a conclusion based on the research question. Is there anyone who need clarification? As this is going to be the end of my lecture for today. Is there anyone who need any clarification? Is there anyone? Before I move to general talk, is there anyone? Is there anyone who need clarification? I'm going to read my chart right now. I'm going to read my chart. So, like I said, I'm waiting for your question. Let me read my chart. Somebody said, why was ROSS output of ANOVA greater than 1? Or 174.25 ROSS. Okay, let me go back to what you're trying to. Now, I don't know what you mean by ROSS greater than 1. What I have here is the residual degree of freedom, 364 and 362. And what I have here is a residual sum of squared, which are these. And what I have here is the degree of freedom, which is just 2. And what I have here is the sum of square. And what I have here is the F. And what I have here is the p-value. Maybe you can try and put your question in the right perspective. I don't really get what you mean by why RSS greater than 1. Because the RSS is the residual sum of square. It can be any value. Residual sum of square can be any value. Okay? But all what I know is that residual sum of squared can not be negative because we call it residual sum of squared. It cannot be negative and it cannot be 0. If residual sum of square is 0, we're talking about perfect model. Okay? We're talking about perfect model. So maybe you can put your question in another word, but I don't really get what you mean by saying why RSS greater than 1. Okay. Okay, so it's only matter that RSS is smaller for model 2 than model 1. Oh, okay. Yeah. Let's go back. You're going to see what I'm talking about now. Now, if you look at the 2 model right here, the RSS for model 2 is less than model 1. I want you to take a look at that. This is RSS for model 2. This is RSS for model 1. Okay? The test statistic that we're doing right here is actually based on the difference between the RSS of model 1 and 2. And with that, we were not surprised by rejecting model 1. Okay? We rejected model 1 based on the p-value. And another thing, look at that. Model 1 has a larger RSS. In fact, it should be rejected. So this is actually confirming the fact that the residual sum of square for model 1 is larger than the residual sum of square for model 2. What do I mean by residual sum of square? Unexplained variation. So it means the error in model 1 is far more than the error in model 2. And that made model 2 to be better. That made the complicated model to be better. Have I answered your question now? Have I answered your question now? Okay. So, good job. So, the residual is smaller in model 2 compared to model 1. Okay. And, of course, the p-value here is actually based on the F statistic here. And you know what? The F statistic here is actually going to make use of this number. Do you know that I can give you something like this in exam and I ask you to figure out this value? How can you figure out this value? How can you obtain the F statistic value if you are given the residual sum of square of the complete model and of the simple model? Okay. Now, this is that's why I showed you this formula the other time. You can see that. So this formula, this is what you're going to use. Plug in the residual sum of square for the simple model here, and plug in the residual sum of square of the complicated model here. Plug in that you know, if you do that, if you use this formula, okay, you're actually going to get 19.061. You can try that. Okay, you are making use of these two right here. Okay, so the F statistic was actually based on the difference between the residual sum of square. Okay, they make use of this model. You can see we're talking about the difference between them. So this is the model that we use. Okay, for them to be able to have the test statistic value here, and for them to be able, of course, you have to make use of the test statistic to be able to get the p-value. Okay, so the story here actually start from here up to this side. Okay, is there anyone who have other question before I go today? Is there anyone? Okay, so this is going to be the end of the class today, and I hope you enjoy my class. I want to come I'm going to be with you again on Monday for another interesting topic. You know what? I'm actually going to upload the materials for next week. And for this today, I'm watch out. I'm going to upload midtime one. I mean the midtime practice question. Okay, watch out for that today. I'm in good condition now. Okay, I'm good now. I think for those of you who want to uh, get in touch with me, you can actually get in touch with me. Okay, so like I said, that is the end of my lecture today. I want to talk about general thing before I finally go. Information about practical assignment 2 and 3 will be released this weekend. Okay, information about that will be released. And then in homework 4, I want to apologize for, you know, uh, including problem 3, because we haven't done that in class. And check the announcement section. I've already sent a message to everyone about that, that problem, you are excused from that problem. Okay, you are not going to do that problem. But for those of you who have spent time, who eventually, if you do that problem, then you're actually going to have an extra credit. Instead of scoring you over 10, I'm actually going to give you 12 over 10. That is in case you have done it, because we haven't done it before. In case you have done it, okay, I'm actually going to give you 12 over 10. If you score everything, it's going to be 12 over 10. It's not going to be the maximum point you're going to have is going to be 10 over 10 anymore. That is for those who have done it, because it was my mistake, and that is the reason why I actually want to compensate you for that. But if you don't want to do it, okay, like I said, you can discard it. You don't need to answer it, and I'm going to mark you based on 10. Does that make sense to everyone? Can you guys hear me?
Yes, yes.
Okay. So I'm actually asking if that makes sense to everyone right now, and that is the situation. So tomorrow the what is it called? The TA is actually going to be with you during the lab section, and it's going to run the lab session with you. It's going to run over some interesting topics. Okay. And then, like I said, I want to appreciate those one who reach out to me, you know, to rate their level of understanding ever since we started. I think I loved your feedback. And then what you guys pointed out, I'm actually going to make sure I work on that, and I'm actually going to improve on my lecture delivery, because at the end of the day, when I give you the information you need, okay, the society, you're going to be good, and the society is going to be good, because I'm actually looking for situation where everybody in the society is going to be good, and that makes society to be good. And that is the reason why, if you are having anything that troubles you, if you get stuck with anything, you can actually set up an appointment with me, and we can, talk it out. Okay. So, like I said, okay, I think I got a shot right now. If we do it, can we get? Yeah, that was what I said. If you do it, you're going to get extra credit. If you do it and you get it right, okay. If you do it and you get it right, you're going to get an extra credit. So it's better if you don't want to do it, no problem. I'm actually going to grade. You have nothing to lose, okay? Because I haven't taught you that topic in class. We haven't done AIC, okay? So if you do it, okay, you're actually going to get an extra credit points if you get it right, okay? So, and that was why I said, okay, in order to be at the safer side, you may decide not to do it. Okay, that is up to everyone. Okay. Uh, in the absence of a question today, I actually want to thank everyone for, attending my lecture today. Make sure you always check the announcement section for updates. Okay, check announcement section for updates. And like I said, check today, there's going to be a midtime practice question. with a solution. Okay, there's going to be a midterm practice question with a solution. If I were you, this is what I need you to be sincere with yourself. I want to tell you this. I'm going to send two separate documents. I'm going to send two separate documents. Okay, one will be question, midtime practice question. Another one is a midtime, another one will be the solution. Another document will be solution to that. But you know what I need you to do, right? You can actually test yourself. You can actually have a self-examination without looking at the solution provided. What can you do? Attempt the question yourself, okay? And you know what? After attempting those questions, then look at the solution and, grade yourself, okay? Grade yourself. For those of you who will sincerely do that, you can actually share if you are comfortable in sharing. You can share that with me, okay? You can actually share that with me. Okay, that is not going to form part of your grade, okay? But you know what? It's more or less like a self-examination, okay? And I want to tell you, I do that a lot. When I was in high school, when I was in college, I did that a lot. Before I wrote an official examination, I used to write self-examination. I put myself under the same examination condition. Okay? When I do that, then I'm actually going to grade myself. Okay? So, like I said, I'm actually going to send you two separate documents. Okay, one for the midterm practice question, and the other one is going to be solution. And if you really want to make an attempt to solve the problem in the midterm practice question, then you can actually check your whatever you get with the model answer that I'm actually going to be provided. But the only thing is that you need to be sincere with yourself, right? Okay. Okay, so I think it's nice talking to you guys today. Uh, I'm going to meet with you again on Monday. Make sure you stay safe. Safe, highly protected. Okay, stay safe, stay protected. Okay, I'm going to see you again on Monday. Have a good day and have a good weekend. Bye for now.
Thanks.